So, I in 2020 I retired and spent a couple of years beekeeping, and then, but I was thinking, what do I want to do? Because I'm 61. I'm very curious about many things, and certainly not ready to sit in front of the television eating bonbons. So I then thought, having spent my career working in advertising, but on the producing side, and some writing, that I'd like to actually go and study some art at school.
Right.
So I went and did an access course, and then got accepted onto the MA course at UCA.
Yeah.
And the things that I've explored that have been of interest to me are what is a moment, and that started from the Japanese concept of mono no wari, which is nostalgia for the moment, and you might have in amongst blossom trees while the blossom's coming off, or equally you might be on a beach and your children are running around and it's a beautiful scene, but at the same time children are going to grow up, the tide's going to come in, you've got to go home, you know, the moment's almost over before it's...
Yeah.
So thinking about moments and then trying to figure out, you know, what is a moment. And it's a small thing, but then I found some Super 8 film which had my first 4.5 years of life on it, and I don't remember any of it. So the only record to me is that. And it's not even through my eyes, it's through a camera looking at me. So in a way, that is a moment to me, because it could be that long or that long, doesn't matter, I don't remember it. That's what I remember. And then jumping on, all right, which is where I'm going to come jump over to you in a moment, time, what has time meant to me? Well, I started working in 1982, and I worked in post-production to start with, and we would do editing and graphics and sound and all sorts of things, and time all had to be locked. Everything had to be locked together, all machines had to be locked together so that you could take stuff from one and put it onto another, or you could lay back audio, or you could lay off pictures to here, but everything was locked to a house clock, boom, so that things wouldn't be slightly offset against each other, or, you know, not work, and things went through time-based correctors to make sure it was all. And then I find that time isn't locked, that time might be different if I'm at the top of a mountain, or bottom of a seabed, or travelling at a certain speed. What is time, and why is it not a constant?
Yeah.
That's... I know so little about it that maybe even the question I'm asking is way too big, or way too vague, or...
I think the question is partly philosophical.
Right.
But there's certainly things physics can say about what is time.
Yeah.
And I mean, I think there's two very interesting aspects to time that come in physics. That is what most people get curious about. One is this idea from special relativity. Yeah. So Einstein's idea is that time isn't absolute. That time can go.
Why? How?
Yeah, but I mean that's one thing. And the second thing is, what is the flow of time?
Yes.
And that's also a very different question, but very, very interesting, because the laws of physics are symmetric. So, I mean, almost all of them are individually symmetric in time. So basically, if you made time flow the other way in the laws, you can follow the evolution as well, and it's exactly the same. So in principle, from the laws of physics, you can, if you're simulating it, you can go forwards or you can go backwards. There's no difference, pretty much. So why do we only experience it going forwards? Why do we only remember the past and not the future?
Yes.
And I think that is a very good question, and that's not something completely answered by physics. But there's a general notion in physics of what gives the direction of time, which is the notion of entropy.
Right.
Because this is one of the things, it's an emergent thing, that the individual laws of physics microscopically are reversible in time, but entropy nevertheless always increases with time. So entropy is the amount of disorder in the system in some sense.
Right.
And the idea is, if you take all the air molecules in this room and you put them in the corner, then you, at some initial time, let them out, they'll spread throughout the room.
Yeah.
and it will come to what we call an equilibrium, and they'll all move, okay? And it will be fine, cool. And according to the laws of physics, you can take this equilibrium and you can go backwards in time and they'll all end up in the corner. The point is they're never likely to do that, okay? And this is one of these things that comes from complexity theory rather than the fundamental laws of physics. That actually, because we start at a low entropy point and entropy can only increase, because there's so many more states that with the air all throughout the room that basically feel the same. So when we say the air is uniform throughout the room, it's not completely uniform. There's a molecule here, there's a molecule here, whatever. But there's so many of them that we're not going to distinguish between the molecules being here, 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 and here, here, here. Okay? They all feel the same to us. Whereas, of course, when you flow them backwards in time, that's going to make a big difference, because one specific arrangement of the molecules will flow backwards in time where they all end up in that corner of the room, and all the other ones won't. And so there's this idea of the thermodynamic arrow of time from entropy. And this idea, which, I mean, then links to cosmology, which is not my area, so I can't add so much about it. But how did we start in this low entropy point? What does it mean? And the idea is when the universe founded from the Big Bang, there was a minimum amount of entropy, and entropy can increase. And as long as it increases, we have a direction to time, but as soon as it ends to the end point, then nobody knows whether time's going forwards or backwards.
And will that happen?
According to most theories, yes. And there is an idea as well that, I mean, it depends on what you think of the universe, because the universe is expanding.
Right.
Okay? And it will continue to expand for our lifetime and our lifetime's lifetime, and I mean for the lifetime of the human race and for the lifetime of the planet. So I mean this is billions of years in the future. The idea is there enough matter in it to stop it expanding, or will it expand forever? And there's certainly a lot of theories, like this was through the 80s and 90s, I don't know the most recent work on it, that said, look, we don't know exactly, it's very finely balanced, but perhaps there's enough that eventually it stops expanding and starts contracting again, because this is the other thing in physics, that gravity pulls everything in, and it's never repulsive. So it's different from all the other forces in physics, which can sometimes attract, sometimes repel, depending on parameters and things. Gravity always attracts in. So the idea is, so long as there's not enough energy in it, or whatever, or power to expand forever, then eventually gravity will win. It will pull things starting to come in and it will contract. And then there's a question, as it's starting to contract, if it's all going to contract to a point, that's a low entropy point again. So now, in principle, if you look at the universe as a whole, entropy is decreasing, which isn't what should happen as you go on in time because of this contraction. And then there's a thought that if you look during that period of the universe, that actually looking backwards in time and forwards in time will be flipped. So actually, if you have intelligent creatures at that stage of the universe's evolution, they'll think back in time is going to what we would call forwards in time, to when the universe has contracted again. And they're evolving in the opposite direction.
Because it's a loop?
Yeah, perhaps. But more a cyclic loop. So
That's
in
right.
one direction it's going this way, and the other direction you're going this way. So they somehow meet in the middle at this point where you have maximum contraction, where presumably on the large-scale evolution of the universe, time stands still. I mean, that's an abstract theory that's the realms of science fiction as much as science, but I mean, it is founded in science.
Okay.
What does physics mean? So, I mean, this isn't practical, but on a large scale, maybe that's what happens. Why do we only remember time one direction? Okay, I mean, we make memories, something goes ahead, and I mean, perhaps that doesn't have to be the same. I mean, perhaps maybe it does have to be the same as the thermodynamic arrow of time, but that's a slightly separate process in the formation of memories. Is what is a memory in the human thing? is that something has evolved and done something to the brain to make that happen.
Yes, I mean, realistically, I don't walk into a room and remember what's happening
Yeah.
then. I mean,
Yeah.
you can have a little bit of deja vu, but that's not...
Yes.
That's not...
Yeah, but according to physics, there's no reason why you couldn't.
That's crazy.
Yeah. In some principle. Yes. Why do you remember the past? I mean, why can't you remember your future timeline?
Because you've not lived it yet. Because you haven't done it
Yeah,
yet.
but I mean, that's giving, again, it's giving a direction to time.
Yes, yes, of course. So, it's possible that everything might have happened, and I just happen to be here on my timeline.
Yeah.
Although,
But then saying it's all happened doesn't make sense. The idea of happened, whatever, is giving a direction to it. And I've not followed the philosophy of this a lot, but I mean, there is certain physics books. I mean, particularly when you start talking about cosmology and things like this, of what is time, and they do come up with these questions. Because the reversibility of time on the microscopic laws of physics is quite interesting, that doesn't happen on the macroscopic law. I mean, you can clearly see a before and after picture, that something's before, something's after in a physical process.
Right, yeah.
And it's not the notion of things falling down, whatever, because I can also throw a book up. If I showed you 2 snapshots of a ball somewhere and a ball another place, you couldn't tell me of this ball which one is the before and which one is the after. Okay?
No, not from a super sharp...
Not from 2 snapshots.
Yeah.
Okay? Because, I mean, eventually, of course, the ball will come down, but I could have thrown it up quite fast. Okay? So, the 2 moments it's going, it happens to still be going up. So, maybe with enough snapshots, you could work out which the direction of time is.
Well, that comes to another interesting thing. You know, if the shutter is narrow enough when the picture's taken, then you won't see any motion blur, and it'll just be super sharp. Which is like the opening sequence to Saving Private Ryan, which was shot with a 45-degree shutter.
Yeah.
So it's super sharp, so everything happens. Do you remember when they used to show golf and they'd use the super sharp shutter, and so you saw instead of the blur? They stopped doing it because it's virtually unwatchable. It's so tiring to watch. They went back to seeing to having the longer shutter. But with the super short shutter on Private Ryan, I went down another rabbit hole of interviewing a whole bunch of people about the 45-degree shutter is 1/8 of a 24th of a second, depending whether you're shooting here or America. So you're only capturing 1/8 of that time. It takes half the shutter for the camera to reset. The other half's available to capture. The deliberate look you wanted, use 45-degree.
Yeah.
So what happened in the other 7/8 of that time? It's lost. It's lost, isn't it? It's
lost.
gone.
Well, you say that, but you can fill it in.
You can and you can't. I worked on a job once, and we were in the colour correct room, and we came to the shot, and the director said, "Looking forward to this shot. There's going to be a gun flash," and there was no gun flash.
Okay.
And it's like, whoa, what the?
Okay.
Where's my gun flash? I saw it through the eyepiece.
Yeah.
I didn't see it through the eyepiece, but it didn't get captured because it was in that.
Because it was too quick.
It was
that's a good point. That depending on the scale, most things could be filled in, but not everything.
Not everything. And so that chunk of time is sort of lost in a bizarre way.
Again, it means what's lost, because in a physics sense, it's never lost.
Mm-hmm.
Because in a fundamental law of physics, I mean, while it's not practical to measure exactly where everything is,
You can't lose
all
information.
atoms, if you could, then you could go back in time and say what happened.
Okay, now I was thinking about that, about another thing. When I came across this Super 8 footage, the footage I said that I saw myself in but don't remember, just as a thing, I thought, well, I don't necessarily want to share that with other people, because if I don't remember it, and I show it to you, you'll know as much about me then as I do, because I don't remember anything about the scene. And
well, potentially, yes.
And so I built a box, and it's laptop size,
right,
and with 2 cross lines and 4 verticals,
right.
So it becomes a thing of 15 squares, that deep, and then I put tracing paper over the top, and place that over the video, and then ran the video, and you just get 15 blocks of colour.
Yeah, I had a little look at it.
It's quite an interesting effect. If nothing's lost, in theory, could you get back from that to the original footage?
Well, no, from that you couldn't. Because, I mean, the thing is...
Where's the information gone, then?
Well, it's gone. It's gone into something else that wasn't recorded. So, in principle, is recorded in the physics, in the molecules, whatever, of the world.
Yes.
But, I mean, forgetting the impracticality of it, in principle, one can go back in time, but in practice,
no.
Again, no. I mean, it's again this. All the information is there to go forwards in time, as we do. Okay? So, in principle, from all of this information, we can predict what's going to happen next, and we can predict it if we have perfect information with perfect accuracy, according to the laws of physics. But, I mean, there's a few issues with quantum mechanics of how this works. But the point is that we'll never have all of this information.
Right. Some of it's gone elsewhere.
Well, it's not that it's gone, it's just impractical.
So it's not collectible.
Yeah, correct.
Put it that way.
Yeah.
Right. Okay. And then
because I mean this is one of these interesting things when you're doing physics simulations. Okay, so you use much smaller systems, whatever. And so long as you're doing a full microscopic simulation, which many people do, so like in my research, which is mostly quantum mechanics,
right,
you would have a quantum simulation, so you'd start with something, maybe you then time evolve it. Or I mean, there's many things you can do, but you can do this. And you can time evolve it forwards, but if you get to the end of it, you could also time evolve it backwards, and you get back to where you started. So if I only gave you the end result of it, you could work out what happened to the beginning, but that's because all of the information is stored of this little closed system. And the point is that I've got this very tiny system with a very small number of particles in it and a big computer. And the computer size would have to increase exponentially for bigger systems. So again, there's this idea that in principle, if you've got a closed room with something in, then you could simulate a life form in it. But the size of the computer necessary to do that would be...
What kind of life form could you simulate in?
I mean, again, in principle, anything.
And how do you mean simulate?
As in, you could put all the information on the computer and it would tell you what would happen in time. I mean, we do all of this all the time in physics experiments, that you can predict what will happen. We're going to do this experiment and we know this is going to happen because we know what the forces are. Okay, we know we've set it up like this, we know what the initial state is, so we can run it on a computer and see what will happen, and then of course you go and check that you're right. Okay, and that you've not neglected anything, because I mean in any real system there's then stuff that you can't control. It's not quite as closed as you can, but many of these systems, like particularly when you get to a modern technology known as cold atoms, they have very small closed systems. I mean, they tend to only have 20 or 30 atoms in or something, so it's really small. You can't get life with this or anything, but you can simulate it, and you can then do the experiments, and they'll match pretty well.
So you have 20 atoms
Yeah.
When you say cold, you mean they've been reduced so cold that they're virtually without energy?
Yeah, basically.
And they're in a space of
they get down to microkelvin temperatures now, so it's really, really cold.
Right.
Okay, and the reason for this is that so they can do interesting stuff. Otherwise, the thermal fluctuations just dominate everything.
So you've got 20 of those in a space. What do they do?
It depends.
What are you looking?
It depends how you set them up. You might be looking for them to form a collective state of matter, so like a different insulating state, or maybe they do something else. Whatever. I mean, usually we look for equilibrium-like states. Okay, so states that don't change very much with time.
So if you're not putting any energy into that, why do they do anything?
Well, because there is some energy there.
Even at that low.
There's always some energy.
There's enough to...
Yeah. To do something, to get into some state. So sometimes you're interested in how you got there, but most of the time it's, at least at the moment, it's more interested in what the state is.
Okay.
So yeah, I mean, but for small systems you can do that, but there's a practical issue and also an accuracy issue of doing it on a large scale, which is due to these ideas of chaos and stuff like this, that the laws of motion are in principle deterministic, so you know exactly what's going to happen. You have the equations for them, but if you don't know the exact initial conditions, then actually what happens could be completely different from what you think it is, because most complex systems are chaotic to some extent.
Okay.
I mean, the motion of the atoms in the room is chaotic.
Right. I get that.
And just because it's chaotic on the microscopic level doesn't mean it's chaotic on a large level. I mean, the pressure is pretty constant everywhere. The temperature is constant everywhere. If there was a small temperature gradient, we know how that would happen. So within the chaos, there becomes order again, but the order then is an emergent phenomenon, not something...
Are atoms moving around within the wood of the wood?
Yeah.
But not very much, or a lot?
Not very much.
Just not very much.
Yeah.
And that's due to forces,
I mean,
electromagnetic
even within the air, they move far less than you think. So it's the pressure waves are fine. What we call the mean free path, which is how long they go before they collide, is actually really, really small. So air at normal pressure, I think it's less than millimeters. I don't remember now the numbers exactly, but I mean, each individual atom isn't going to move far before it bounces off another atom, comes back again, and it will kind of mostly move around its own little space. For the atoms in the wood, it's going to be more of the order of nanometers that it moves. Okay. So it's orders of magnitude less, which is why wood is hard and air is a gas.
And so lead even less.
Yeah.
That's why it's so dense.
Yes.
Okay.
They move around, but not very much. This is what we would call in physics thermal fluctuations. So in some sense, everything is always in motion. A snapshot is a snapshot, but...
So within a regular snapshot, time being at 1/2 of a second, there's still a bunch of motion going on.
Yeah, there's huge amounts of motion. So everything in physics, you always ask, what's the time scales involved? Because at different time scales, different things are happening. And the time scale for microscopic motion is far, far less. So I don't know if you saw the news announcements of the Nobel Prize this year in physics, which is for what they call attosecond spectroscopy.
Oh, okay. So what
I'm trying looking at really fast motion. So at that level, they can actually see the electrons going around atoms and things like this.
I try and read Quantum magazine.
Right.
And sometimes when I'm reading it, I feel like I'm understanding it, but 5 minutes later, I did not get that. The attoseconds, are there not more attoseconds in a second than there have been seconds since time began?
Correct. It's about the same. I mean, this is really short time scale. But this is the time scale on which an electron will orbit an atom. So, I mean, atoms are made up of electrons orbiting nuclei.
And we can measure that.
Yeah, but, I mean, this is very recent research, which is why they got the Nobel Prize this year. I mean, it's been developed over the last 20 or 30 years, but it's really, really new and only just being applied to do measurements of interesting things rather than a proof of concept.
And what kind of things would you want to measure with that?
Well,
I mean, not how long I take to eat dinner.
Yeah, no,
Clearly,
but the motion of electrons within things. I mean, even the motion of atoms is going to be slower than that.
Mm-hmm.
Okay, so you can resolve the motion of atoms with far longer timescales. So it's the motion of electrons in atoms and around solids and things like this that you'll be starting to see when you look at this. Very short timescales.
That's extraordinary.
Yeah, it really is. But it really does come to this thing, what do you mean by a snapshot? Because a snapshot, in physics, a snapshot means a single instant in time with no time scale whatsoever. But of course, that's in a theoretical argument of saying, look, this is exactly what's happening at this time. But in any practical sense, there's going to be a timescale involved, and the timescale, there's very, very different things, even if they're all built up from the same physical laws.
So an attosecond would be the shortest measure. That would be your
Well, that's
closest.
the shortest measured so far. If you go to even shorter ones, then who knows what we might see.
Okay, we're getting somewhere that I feel I can come back in a little bit.
Yeah.
A little bit. So an attosecond is the closest you have to a snapshot, a proper snapshot, a physics snapshot, as you said.
So far, yes.
So far.
But of course,
Then
the point of doing it is not to get the snapshot, it's to measure the motion on this scale.
I get that. But then, are you also saying that you think there might be some granularity to time? That there is a thing beyond
okay, that is a
you
question.
can't-
So people propose this. I'm not in that field of research.
Mm-hmm.
But people propose there might be a shortest possible time. There's this time scale known as the Planck time.
Right, yeah.
Which is, I mean, makes the attosecond look long.
Mm-hmm.
I mean, this is ridiculously short, so we're many years off, from ever measuring this.
Right.
But, I mean, at that time scale, we actually just don't know what's happening. That's where the current knowledge of physics breaks down, and that's why people propose some of these ideas. Is time really continuous or is it granular?
Mm-hmm.
I mean, it's the same with the lens. You can get the similar thing called the Planck length. And this is just things you can make up of the fundamental constants of physics, like the speed of light and Planck's constant and whatever. And you can make these things and you say, look, this comes out of it, but what does it really mean? Okay, what happens at this scale? And of course, that's part of the goal of all these big particle accelerators, is to say what happens. Because we just don't know. There's theories, but who knows? It might be granular, for all we know.
So going back to the very beginning when you mentioned special relativity, why is time not constant? Why might it be different? Why might you experience it differently than me? Why does going fast appear to slow time down? Or why does the edge of a
Well, I mean,
black hole...
why is a difficult question.
All right, no.
Because
Okay.
why is, I mean,
okay.
that's
Sorry,
what we
that's
measure. That's the laws of physics.
Yeah. How?
So, I mean, if you've come across the twin paradox, I guess, which isn't really a paradox. Right? But, so the idea is you have two twins, one goes off in a spaceship.
Right, yes.
Okay,
And we come
goes
back.
very fast, comes back,
Yes.
and that twin is now younger than the other twin.
Yes, yep.
And that's totally correct. Okay, this, I mean, obviously not measured with twins,
Sure.
because you can't send them off so far, but on other scales of of again, atomic level things, you can see this happening. And so, I mean, it's absolutely true. And I mean, another one of my favourite example is that my dog wags her tail a lot. That means the tip of her tail is very slightly younger than the rest of her.
How?
Absolutely irrelevant in terms of the scales.
Sure.
But it's kind of weird to think of it.
And the top of my head is younger than my toes, right? For being slightly further away from the
correct.
centre. How? What causes that?
I mean, it's just an effect of physics. That's how you measure it. But there's another way in which it's not as unusual as you might think. And when you're saying, look, how old is something, okay, you're basically saying, look, I've got a time now, I've got a time then, how much time has passed between them?
Yeah.
Okay? And that's fine, you've got a timeline.
Yeah.
But it's very similar. So if you think of time as purely one-dimensional and not embedded in space and all and things, then, I mean, the only way to do it is subtract one from the other. That's the only distance you've got, because that's the only way to get from here to here.
Yeah.
But if you have 2 points in space, for example, okay, and you say, look, I've gone from here to here, how far have I gone? Well, it depends on the route you took. That's not something that's surprising at all. If you walked directly here, you'll have gone a shorter distance than if you walked in a route like that.
Right.
Okay? And the whole idea, if time and space are intertwined like this, any question like, how far have I gone to get here, depends on the route you took, but then how far in time did I take to get here, depends on the route you took as well. And so as soon as you accept this premise of special relativity, that space and time are not completely independent of each other, then it makes sense that the path will determine the distance.
So if this is space and time,
Yeah,
and you and I are both here,
yeah,
and you stay at home and go here,
yeah,
travelling
exactly.
on the Earth, and I whiz over there,
Yeah,
God knows how far away, and then whiz
Yeah.
back and rejoin you. In terms of the universe progressing through its space and time, I've gone much further than you to arrive back here.
yeah, correct. You've gone further in distance, but less far in time.
How have I gone less far in time? That's what I'm not.
Again, that's just, I mean, it's the maths is a little weird of it. But, again, it's just this idea that time isn't absolute, in that the time experienced by me is not the same as the time experienced by you. It depends on the route. Just like distance depends on the route.
So,
Yeah, no, I mean, it's a weird because we have this idea of absolute time in our head, but I mean, you get round the idea of absolute space by the other dimensions. And so if we're both here and then I meet you at some other point later, okay, somewhere else, then it's perfectly natural to say, look, the distance we've travelled between our last meeting and now isn't going to be the same. Because we might have taken different routes to get there.
Yeah.
Okay, so why is it so different to say that with time as well? The time distance isn't the same. So time and distance are separate in special relativity. They're not completely equivalent, but they're also linked. And as soon as you link them, if you say something for one thing, then why it has to be true for the other as well. But of course, to a much lesser extent for time.
I think that the problem I'm having there is I'm thinking you and I are going by the same clock, bound by this thing, and then
Yeah,
I peel off and
but
go
the clock
over
isn't
here.
absolute.
I go over here and come back.
Yeah, you have a clock, I have a clock. Why do they have to be the same? You have your distance counter, I have my distance counter. Just think of measuring time with a clock as the same as measuring your distance with a, whatever it is, a wheel you put in front of you.
So is it almost like time and distance are going to add up to X, and if I'm going much faster, then I'm using up some of that X, using up more of that X for distance, so time is less, or what?
In some
this
sense,
is why I'm not
yes.
on your course.
Yeah, no. In some sense, yes. It's not just adding them up. There's a different thing, but
Sure.
there's. I mean, we build a lot of physics around these things we call invariants. So there is something called proper time, which is constant for everyone. Okay, I mean, which is very much like this idea of really properly measuring how far you've gone. Okay, so not just saying, look, we're here, I meet you again in Newcastle or whatever, that's 300 miles away, therefore we must have each travelled 300 miles. Okay, because we haven't. We might have gone different ways to get there.
Sure.
And I mean, you can do the same for time, but because time and space are linked in special relativity, and I mean, you can go through the ideas why they have to be linked, but as soon as you say they're linked, then it makes perfect sense that you say, look, the route I take to get from here to here affects my distance travelled to get from here to here. I can't just say this is the start point, this is the end point, therefore the distance is this, because that's not, it depends on the route. And the same has to be true for time as well. So I mean, I'm trying to avoid going through the full derivation of everything, but just trying to say, look, as soon as you accept time and space as linked, then it's not as unusual a concept as it might seem.
And either why or how are they linked?
So that, I mean, this is a good question. They're linked because that's how physics is.
Sure.
Okay.
Yeah.
That's the cop-out answer. There was a lot of experiments. So this is the late 19th century when people really started to understand this. And the way they understood it is they were looking at light in particular. And this idea of, look, light, we'd finally understood then that light is a wave, okay? The same as sound is a wave, okay? So you're asking, look, sound is a wave, a pressure wave in a gas. Or, in fact, a solid. You can travel sound through a solid or something, but there's a pressure wave of something, and that's how you're transmitting it. So light is a wave, but is a wave in what? Okay, what's the thing that's waving in that sense? In order to understand it, which we understand in sound.
I don't know. What is it waving in? I mean, if it's out there in space, what?
Yeah, that's the question. So they proposed this thing called the ether, as they didn't really know what it was, but it's the thing that light waves in. And I mean, that was a perfectly sensible thing to do, because I mean, you may not know exactly what air is, but if you want to say, look, I understand sound is a wave of some form, then I'm going to say air is the thing that's waving. Okay, and then you can go away and you can work out properties. But then there's various things that must be true. So, for example, if you're traveling through the medium, then the speed of the person sending the sound or the speed of the observer through the medium is going to slightly affect the way the wave works. Okay, so if you're traveling through the air at some speed, then the sound travels at some constant speed in the air, but because we're walking through the air where there's some wind, it's travelling at that speed in the air, but because the air is moving with respect to us, we feel it slightly quicker. I get to the end result slightly faster, so you can measure the speed of sound, but that's going to be in still air. If you then have the air moving, the speed of sound is going to be added or subtracted to that amount the air is moving. Okay, and because speed of sound is about 1,000 miles an hour, sound I would have to move pretty fast for it to make much of a difference, but you can measure these things. So they tried to measure the same effect in the ether, they basically said, look, we don't know what's waving, let's call it the ether, but what we can do is measure the speed of it. Because we can measure how fast light is going. If we're travelling in one direction, we can measure how fast light is going if we're travelling in another direction. And I mean, the directions they used was the Earth going around the sun one way and then the other side of the sun, okay, where it's opposite directions. So presumably you're travelling in opposite directions through the ether. And let's measure the difference. And some guys called Michelson and Morley did this, which is a very famous experiment in physics. And they detected no difference at all. Light was travelling at the same speed all of these times. And I mean, then they repeated the experiment 20 years later with more sensitive equipment and again found no difference whatsoever. With the understanding is they knew how fast the Earth was going, they knew how fast light travels. And they knew their equipment was sensitive enough that it should have picked up the difference. So the end result of this was that there can't be an ether. Even if we don't know what it is, it can't be there, which means that light is waving in nothing. There is no medium. There is nothing light is waving in. And then how do you resolve this? And this is where Einstein came in with his special relativity and said, look, this can happen, but only if we link space and time in this way. Otherwise, you need a medium for the wave. And of course, then lots of experiments were made and he turned out to be right. But it was a crazy idea at the time, and it still is a crazy idea because it's just so far outside our own practical experience. Maybe it's part of a bigger picture, but...
So is time the medium?
No, there is no medium.
There's just no...
Yeah.
It just does.
Yeah.
It just does.
Yeah, it just does. But that basically means, look, people are travelling at different speeds. Light always travels at the same speed no matter what's happening, which means it's not adding and subtracting in the same way as you'd expect, which basically means time and space must be linked in some way as to make light always go the same speed. And then you work out the maths of this and you find these effects like time dilation and whatever.
And what does time dilation mean?
It basically means that if you're travelling faster, then time moves slower, yeah.
If I'm on a plane going 1,000 kilometres an hour and I shine a light forward, why isn't it going at the speed of light plus 1,000?
Again, this is the idea of relativity. You'd expect it to. If there was a medium it was travelling through, it would be. But if there's no medium, then why should it? Okay?
Because you've put extra energy into it.
No.
No.
I mean, it's this idea of what's travelling through a medium and what isn't. So, I mean, if there's a medium, there's an absolute thing where you can measure what's the speed. Okay, so the speed should depend on how fast you're travelling through the medium. So you say, look, how fast is light travelling? I shine it here, whatever. But suppose I toss a ball to you at some speed. Okay, and then I go on in a plane and I do the same thing. From the point of view of sitting on the plane, you won't know you're on a plane.
No.
Okay, I've tossed the ball, it's exactly the same. There's no difference in speed because we're happening to be on a plane because, I mean, it's relative to me that it's happening, not relative to the medium. If you're on a plane, you also won't notice the speaking because the air in the plane is moving the same. But if you're on an open top plane, then you will notice the difference. Okay, then it will be hard to speak to people even if you forget the sound of the wind.
Got it. So we're on a plane and you throw me a ball and it just feels like regular you throw me
exactly.
a ball. My mum's on the ground and miraculously can see through plane bodies.
She can see the ball going faster.
She's going to see the ball.
Fine. Yeah. But the point is, if there was a medium for light, then even just being on the plane, we should be able to measure that. Because the plane is travelling through this medium, unless the medium, like the air, is travelling with the plane. But, I mean, that's not likely. Not for something that light is travelling through, that we can't measure otherwise. Because if we could confine it and move it with us, we'd be able to measure it. So, I mean, this is how Einstein came up with the ideas. They were crazy. If you read history of physics books, far too many of them, in my view, talk about these people who believed in the ether back there as the thing that carried light. And, I mean, just goes on about they were all wrong and things. Yeah, well, true, they're wrong. That's correct. But it was by far the most sensible idea at the time. The idea of no ether and light waving in nothing is much more weird, and no one would ever have believed that unless they'd conclusively disproved by experiment that there can't be an ether.
Well, I think we're frequently not very good at writing history from the point of view of...
Yeah, I know, yeah, no, you do this.
That's what we're talking about there, isn't it? That back then...
Yeah, back then.
But, like, hey,
but I mean, there is also many points in the history book, like Galileo and his sun travelling around the sun. And I mean, with the experiments they had at the time, it was clear he was right. And I mean, there's also then societal, whatever it is, resistance to change.
Yes.
Which is fair enough. So that was the people really not thinking clearly. I think there's an argument to be made that people should have listened to Galileo. He was saying sensible scientific stuff, but you cannot make the same argument about the ether. This is my point. The ether, okay, it didn't exist, but we had absolutely no reason to believe it wouldn't exist. That's by far the least sensible option if the existence of the ether is still a possibility. You have to conclusively disprove the obvious solution to a problem before you can come up with the weird ones. Which, I mean, but that's just the evolution of history of science. That's going a little bit away from this idea of time, but yeah.
One other question that isn't quite connected to time. I suppose it is in some ways. If, as the universe expands, is there energy inherent to the fabric of space? Is more dark energy appearing, or what? Well,
that's a good question, and nobody knows. Is the short answer.
And if it is, where's it coming from? I mean, that sounds like a free lunch.
Yeah, but I mean, there's a lot of interesting questions, and again, my field isn't cosmology, so I know the basics of it, but I don't know all of the latest.
It's more than mine, right?
Yeah. But the conservation of energy is one of these crucial concepts in physics.
Yeah.
But it's very interesting to go back and look, why do we expect energy to be conserved? And the idea is there's a absolutely wonderful theorem by a lady called Emmy Noether, who you should look up if you get a chance. She's Emmy Noether, Noether. And I mean, she had the misfortune to be working in Germany at the beginning of the 20th century as both a woman and a Jew, at a time when both women and Jews were banned from having jobs at universities. So, I mean, but she was so good that they hired her anyway. And I mean, it's a pity she's not a household name, but most of her work was technical. But she made one of the most important contributions to physics ever, is she found that all of these conservation laws, so conservation of energy, conservation of momentum or things like this, or conservation of angular momentum, anything that's conserved was linked to a symmetry. And if you knew what the symmetry was, you could get a conservation law out of it. And the conservation of energy is linked to the symmetry of time translation. So this really is to do with time. That the laws of physics now are the same as the laws of physics tomorrow. That's a symmetry, because time moving doesn't change anything. And you can then prove from that, and it's unfortunately a mathematical proof. I really do not know of a way of properly explaining it without the full maths. But you can derive from that energy must therefore be conserved. And that's beautiful, because you have the most simple possible thing starting with that we expect the laws of physics to be the same every day. Okay, we don't expect Newton's law to change with time.
No.
Okay, the position of things do, but the law doesn't. And as soon as you do that, you get this conservation law out, and I mean, this is what we call energy. The issue in the cosmological scale is, while the laws of physics may be constant with time, there's obviously something different as the universe is changing. So this homogeneity of time is not necessarily any longer true, and therefore energy is not necessarily conserved. So actually, on the scale of the entire universe, we don't need to conserve energy. Not necessarily. Because if you assume the universe is some closed object that's expanding, then it is actually changing each day.
Yes. Yeah. No, yes.
Yeah. And then you can... And yeah, then this is where I've never really studied it in fields of cosmology, is how much does that affect cosmology. But there's other issues there, though, that with gravity, for example, the further apart things get, the higher the energy. So if they get closer together, there's a very low energy, because the attraction is reducing the energy. Okay? I mean, if you think about potential energy, if you go up, that costs energy to get up.
Yep.
Okay?
Yep.
So it's going to cost you energy to get out of this big gravitational well.
Yeah.
Okay? So as the universe is expanding, things are getting further apart, and therefore they're getting more energy in some sense, because they're further apart.
Because they're being pushed.
Yeah.
Or moving, whatever.
Yeah,
Whatever.
exactly. So I mean, that's another way of thinking of it, and I know people do study these things in more detail, but that's where my knowledge becomes more hazy of this. I've never looked.
Well, that was fascinating.
Yeah.
I think I understood a little of what you said about slices of time getting smaller and smaller.
Yeah.
If time is something you can slice, I don't know, but measurements of it.
Yeah, measurements are getting smaller and smaller. Maybe there's an eventual limit
yes.
where measurements can't get smaller and time becomes discrete, and many people do believe this will be the case. But it's theoretical at the moment. It's far off anything where we can confirm.
But might that be a problem of measurement rather than...
Well, I mean,
any
no. This
granularity
is the question, that people think it really is something theoretically possible, but we haven't measured it. And I mean, this is one of these things that once you go from maths to science, this is interesting. Mathematically, you can say all the things that are possible, and you can say all the things that are consistent with what we've currently measured, and they're all valid views of the universe. But then you have to be able to measure something in order to say, look, which one is our universe? What are the correct laws of physics on this scale? And on these very, very short scales, we just don't know. So, I mean, what is an instant? One can say on different time scales. And I mean, read some of the stuff written about the recent Nobel Prize. This year, because the attosecond is as close to an instant as we can get at the moment. That doesn't mean it's a fundamental limit. No one believes that's fundamental. As technology develops, maybe we can get shorter. And I mean, if you go to the Planck length, I mean, you already said, look, there's as many attoseconds in a second as there is seconds in the universe. There's as many Planck time scales in an attosecond as there is attoseconds in a second. I mean, it's another 18 orders of magnitude beyond that. So we're nowhere close to a measurement of this. So down to that scale, people would be very, very surprised if anything became different. But once you get to that scale, we just don't know. On the Planck time scale, maybe things start becoming different. That becomes now the realm of philosophy, science fiction, whatever, for now. Maybe another few hundred years of technology will know what to do to get there. But at the moment, it's so far outside the range of current technology that...
That's fascinating. I've worked with a thing called a phantom camera, and that would go to 145,000th of a second, which seemed like an extraordinarily precise and tiny amount of time, but it's really not, is it? It's nothing to...
No, nothing compared to these. There's, I mean, if you look at YouTube as some physics videos, there's people who do a lot of things with very high-speed cameras.
Yeah, no.
So they look at bullets going through glass and things, and looking at the glass breaking and whatever.
Yeah, and we used to do that. We used to shoot some stuff like that. And it's amazing how much stuff is happening at such a tiny...
Yeah. But I mean, every scale you go down, this is one of these interesting things, is that at every scale you go down, there's more different stuff happening. And not just other stuff happening, but different stuff happening.
Mm-hmm. Yeah.
Which is cool, so...
Well, that was brilliant. Thank you.
Yeah,
Thank you very,
interesting
very,
discussion.
Very
Provoking,
much.
certainly.
Well,
I don't know how much it helped with anything.
Interesting for me. I don't know about you.